SwayamPrabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 20. We covered wall friction as well as the velocity distribution, the effect, the kinetic energy effect because of velocity distribution in the last module. Here we would like to cover the energy loss because of sudden change of direction or even entrance effects which would happen typically when a cross sectional area of the conduit suddenly varies, it expands or contracts. So that's also a sort of directly related to the flow regime, and there may be different entrance effects imposed because the flow obviously being laminar and turbulent. So we would like to now sort of estimate this empirically. Again, we'll borrow some of the principles from fluid mechanics. So friction losses also occur due to a gradual change in the flow direction example in a 90-degree bend and similarly fitting. So fittings may be expansive or contracting in nature, as we'll illustrate just a little bit later. So the associated frictional loss is accounted for by using again the energy balance equation. Bernoulli's equation. With an equivalent factor L by D for the bend. The frictional loss per unit mass associated with a sudden enlargement or contraction of the flow cross section or flow area is, let us say, EF2, just as we had EF1 for the wall friction effect earlier. So this can be recorded as half EF V dash square, where again V dash is the average velocity, average flow velocity, in the smaller cross sectional area. Supposing the flow is expanding, let us say like this, where the area is changing from a smaller area A2 to a bigger area A1. So, the average velocity would be the entrance velocity to this expanding flow, and for the contracting case, where the flow is coming from a bigger area to a smaller area again, it would be the discharge flow that we will be talking about. So, the value A2 always, which is the smaller area, is the value of cross section where the average velocity needs to be recorded. And obviously, EF is the friction factor, is the loss factor, I would say, because of this bending and the expansion contraction effects, etc. And the way that you look at EF is really plotted right here, and this is again two very important trends which are borrowed from elementary fluid mechanics, where we talk about the energy loss because of bending or contraction as a function of the area ratio. So, for the sudden expansion case, as you can see, there is a regime corresponding to the turbulent Reynolds number varying between 3000 and above, and the EF is plotted here as a function of the area ratio A2 by A1. So, obviously, for sudden expansion, the A2 is going to be the entrance area, and A1, like you can see here, and A1 is the discharge area, and so therefore, this A2 by A1 can be maximum 1, and otherwise it is going to be less than 1. So, the same thing happens for Reynolds numbers which are in the laminar zone. So, the L by D, which the term which is coming here particularly for the laminar flow case, is, you have to remember, this L and D are the length and diameter of the smaller cross section. That is how the data has been recorded, and these are sort of empirical data which are recorded again through just looking at the energy balance across such expanding or contracting fluid channels. So, for the sudden contraction case, again the same is recorded as laminar and turbulent, as you can see, and this EF really is the loss factor that comes because of the bend or the change in the cross section. So, for laminar flow, the length L and diameter D, as you can see in most of the cases, whether it is an expansion or contraction, you have a inclusion of this L by D factor here, are that of the smaller cross sectional area. The value of EF depends on whether the flow area is enlarging or contracting in the flow direction, and the value of EF for a sharp change in the flow cross section can be recorded as in these two graphs shown here. So, obviously, depending on the type of entrance, there is also a entrance effect which is added onto this friction factor, where this EF term gets slightly modified because of such entrance effects. So, let us look at this entrance effect. So, for a straight entry case, the EF obviously is the EF that you are recording. So, whatever EF data you are recording with respect to the area ratio is, for the straight entry case, the value of the actual loss factor, and the value for a projected pipe entry, as you can see here, where this pipe comes out from this entrance into the mold. So, maybe the pouring basin is right about here and the flow is happening in this direction. So, in this kind of a situation, the EF that is recorded really is twice the value of the EF that is observed from the change in the area ratio as in the last figure, For the case where it is entry with rounded corners and there is some kind of a radius effect which is involved here, and r by d is typically 0.1. So, for that the EF is recorded as a third, 1/3 of the value which is read from the plot on the area ratio versus EF, and then for the tapered entry again the modification that you have is a sixth of the EF value that is read from the graph of sudden expansion and sudden contraction effects. So, I am going to use these more appropriately when we actually numerically design this problem and try to see what is going to happen to the overall energy balance between the point 1 and 3 in both the vertical and the horizontal gating system. So, as of now the values of EF for some other type of changes in the flow geometry, where EFS refers to the value corresponding to the sharp change in the geometry with the identical initial and final dimensions. So, now let us go back to the again the vertical simple vertical gating system and try to modify the energy balance here. So, let us modify the energy balance equation between points 1 and 3 after accounting for all the losses are principally three kind. One is due to change in kinetic energy due to velocity distribution, change in kinetic energy due to friction of walls, and that due to bends or fittings. So, these losses are because a sudden contraction of the flow path between 1 and 2, as you can see here. Okay. So, the energy balance at 1 can be written down as P1 by rho m plus velocity head is 0 as assumed earlier. The velocity V here at the top of the particular pouring basin is assumed to be 0. The metal is too large a quantity for any substantial change in the height to happen at this particular juncture, plus the potential head which is GHT in this particular case, HT being the height of the top of the pouring basin from the mold. Okay. So, that becomes equal to P3 by rho m, P3 being the pressure at the juncture 3 right here, plus the kinetic loss which happens because of velocity distribution effect. So, we write this as square of the velocity by 2 beta, where beta again would have a different value when it is laminar and another different value when it is turbulent in nature, the flow is turbulent in nature, plus the loss EF1 which happens because of the frictional loss of the wall, plus the EF2 which is the loss because of the bends or the fitting. So, that is how the energy balance would finally happen. As you can see here, there is no potential head really. So, height of the mold as assumed here at point 3 is basically equal to 0. It is a top gating system. So, that is how we have been doing this analysis earlier as well in the case where there was no friction. So, on the right side at the juncture 3 you are accommodating for the loss due to the velocity distribution, the loss because of wall friction and the loss because of the sudden contraction and expansion. In this particular case, between 1 and 2 there has been a contraction, and because of that there is a loss. So, this loss has to be taken in the overall energy balance equation for good analysis, and V 3 is really the average velocity in the sprue and I also further assume that the mold is open to the atmosphere. So, P 1 and P 3 are similar to each other. So, because of which the pressure heads get cancelled out, and I can further write down the E f 1 as the total amount of friction loss, which is actually given by 4 f L by d V 3 square by 2. V 3 is the velocity equal to V 2 of this particular section of the top gating system, which is the sprue section. You know that this is a continuous area, constant area geometry, where whatever be the inflow would be the outflow for mass continuity to hold true, and E f 2 is basically the frictional loss associated with the sudden contraction. In this particular case, the contraction happens from the section 1 to the section 2, and beyond 2 there is no other such contraction which takes place. So, we are just considering the potential, the energy just at the point of exit of the metal from the sprue to the mold, and so this E f 2 comes out to be half E f V dash square, where E f again is has to be obtained from the plots for the energy loss E f with respect to the area ratio for sudden expansion or sudden contraction case, and these all values, for example, E f or f depend again on the Reynolds number of flow, or whether the flow is laminar or turbulent in nature. So, the final expression which emerges in this particular case comes out to be G h t on one side, and then we have V 3 square by twice beta plus 4 f L by d times of V 3 dash square by 2 plus E f times of again V 3 square by 2. In other words, if I just simplify this out, it becomes twice G h t equals V 3 square divide times of 1 plus beta plus 4 f L by d plus E f, and I think we have earlier clearly illustrated that this length L is the length of the smaller diameter of the sprue and similarly the d is the diameter of the sprue. So, in this particular case, it is really a case of contraction, where from 1 the flow is submerged or converging into the section 2, and as you can see that there is a contraction in the area, and in all such cases you always have to assume the length and diameters of the smaller area of cross section. So, in this case the smaller area of cross section is at 2, and so we assume the length and diameter of the sprue for calculating this loss, contraction loss of the fluid. So, from this particular equation now, then you have V 3 dash becomes equal to some coefficient C d times of twice root h t, and the C d is very popularly known as the discharge coefficient from elementary fluid mechanics, and this is represented as 1 by beta, the loss term because of the kinetic energy change due to velocity distribution, the loss term because of bending, contraction, expansion, so on and so forth, plus the frictional loss in the pipe, which is 4f L by d times of to the power of minus half. So that is how you define the discharge coefficient, and as I will say, I will kind of show you in the following iterations that the discharge coefficient here can be generated in an iterative way, because at the outset you probably just have a first guess of the Reynolds number, and that may not be the accurate velocity, because the velocity has to go through all these different terms. So the earliest assumption that you can make, if there is no loss factor, that is CD equal to 1, is that V3 converges into rho 2 GHT, which is in fact the same term as you had seen in the analysis where we neglected the frictional effects, and then starting from there and then trying to see what is the flow regime, whether it is laminar or turbulent, we can try to estimate iteratively what is the CD value, so that the actual values of V3 could be slowly sort of converged at, and so with 2 or 3 iterations you are able to come to a point where you can have a perfect convergence of the V3 term here while doing calculations for such molds. So if supposing in this analysis we would have assumed a bend or a fitting, so if the sprue also had a bend apart from the normal contraction losses that you can see here, which is typically the case in most of the applications where you want to avoid putting all the metal on the top of the mold. Mold is a very fragile mold has a very fragile constitution, and typically made up of a refractory material. So it is sometimes advisable to not have the gating arrangement which includes the pouring basin or the sprue just over to the mold. Rather, it is preferable that you have a misaligned pouring basin and sprue somewhere here, and you have a bending provided in the pipe which connects and still makes it top gating, because the gating provides the material flow at the top of the mold right about here, and everything else can be starting in an off shifted manner from the actual mold cavity. So from an engineering perspective, that becomes a pretty good exercise. So if the sprue also had a bend or a fitting, then this factor EF1 would change, and the change is again represented in terms of the equivalent loss that would be affected by the fitting itself. So this is the L by D of the wall friction of the smaller cross sectional area, as I had discussed before, and this L by D equivalent, which is a new term which has been added here, this is actually a fitting specific term and or a bend specific term, and there are many experimental analogies which talks about what this L by D equivalent is going to be. So basically, if supposing there is a bend of a certain dimension, there are maybe data tables which are available about, supposing there is a particular kind of bend or a kind of fitting, what would be the L by D equivalent in that particular case. So this would definitely contribute to an increase in the total friction loss, and thus the whole equation now of the CD would be written down as CD equals 1 by beta, as I had illustrated earlier, plus the small ef, which is the loss because of the bending or the fitting, and then there is a frictional loss imparted by the bending or the fitting, which would be actually 4f times of the L by D wall friction effect plus the L by D equivalent loss due to friction at the bend or friction at the fitting, which would come up to the power of minus half, and so that is how you typically make the discharge coefficient and iteratively progress to find out the range of the flow, whether it is laminar or turbulent, and then arrive at a certain value of C d. So, I am going to now close this particular module in the interest of time, but in the next module I am going to definitely try and tell you some practical problem in which we can estimate what is the C d value and also what is the velocity of flow. So, thank you so much.